Math.
Wait.
Yes! Yes, you got it. So, lesson, sorry, I didn't mean to scare you. Capacity. How much, what? How much can it hold, right? So we think, what about soda and milk? When you buy soda, typically, what are the units? You don't buy gallons of soda.
A liter.
Liters. Liters. Okay? So there's a table on page 415 that talks about the two different systems of measurement. Okay? The one we all use because we're the U.S. and we're smart or dumb, depending on how you look at it. Okay? The U.S. customary. Okay? And the reason people who don't like it is because it doesn't have a simple numerical base like the metric system does, okay? So the metric system is all about tens of things, okay? And so the only one we're gonna learn here, 1 liter, that's equal to 1,000 milliliters or milliliters, okay? But for us, it's customary or normal for us to talk about 1 gallon. That's equal to 4 quarts. And I think if you're in cooking class, do you do some of this? All right, 1 gallon. 1 quart is equal to 2 pints. 1 pint is equal to 2 cups. And then 1 cup, and you look at the numbers and you think, it's going to be 2, right? No, it's going to be 8 ounces. 8 fluid ounces, yes. So this is one of the complaints that people have about the U.S. customary system is different ratios. There's 4 quarts in a gallon. There's 2 pints in a quart, 2 cups in a pint, 8 ounces in a cup. I mean, then you get the tablespoons and teaspoons, and it's just really weird from there too.
Just remember 8,224 or 4,224.
All right. So you can kind of see why people like this. We can go to centiliters, deciliters here very easily. It's just by multiplying and dividing by 10. But all we're really going to be thinking about is how do we solve problems with this? Right? If you got my first statement about how units matter, because it matters what comes after the number to indicate what size quantity we're talking about. Okay? So if we take a look at just an example, we'll just say which is more. Let's do let's do 12 quarts or 17 pints. Okay? So we're going to compare the quantities. In order to compare the quantities, we have to know, camera keeps falling back. We have to be able to convert them to the same unit. In the same way that when you add or subtract fractions, you have to have common
Denominators.
Here, you got to have the same unit. Yes, ma'am. Yeah. So, 12 quarts or 17 pints. What we've got to do is convert them both to quarts or both to pints. Does it matter which one? Does it matter which one?
Yes. No.
It does not. As long as you change them both to the same unit. So, if we look at our conversion here, 1 quart is the same as 2 pints. So, we could change 12 quarts equals some number of pints. Here's what I'm going to do. I'm going to write that statement. Yeah, I hear the right number here. But I want to give you some substance that's going to affect how you do this for the rest of math and once you get to chemistry. Because you have to change units a lot there. So 12 quarts, what I'm going to do, I'm going to multiply by something that shows me the ratio of pints to quarts. What is it? Well, up here it says 1 quart is equal to 2 pints. And I want pints in my answer. I only want to have pints. So, what do? I'm going to put 2 pints on top, and I'm going to put 1 quart on the bottom. Now, what is the blue part equal to? What is the blue part of my equation equal to?
Division.
It is division, but what is its value? It's more.
2 pints.
What do you know about 2 pints in 1 quart?
2 pints go into 1 quart.
They're
4 to 1.
they're what? If they're equal, therefore the blue part is what number? 1. So this blue thing, this entire thing is really just a 1, isn't it? Anytime that you multiply a number by 1, does it change?
No.
No. So I'm finding the same quantity in new units. Again, same quantity with new units. Okay? So it's like I took the bottle it was in and I poured it into a different shaped bottle with different markings. Okay? So you've already told me the answer. The answer is what?
24.
24 pints. Now look, pints was what I wanted, so I put that in the numerator. What's going to happen over here if I have quarts on top and quarts on bottom? They're going to cancel out. You see quart divided by quart. That's 1. That cancels out, right? So let me give you a visual for this. Okay? Let me give you a visual for this. Suppose we had some quantity and it was 12 pints, and then I poured it into, you don't have to draw this, and then I poured it into like a skinnier tube, and it's that's supposed to be 12 quarts, isn't it? Well, P turns into a Q really easily. 24 quarts. What I'm hoping you guys are seeing, and again, this is a crude picture here. I was having this conversation with my 6-year-old, who always complains that her sister got more milk. And I said, honey, the shape of the cup is different. That one's higher. Right? When you look at these two containers, right, what I'm trying to convey is that they're the same quantity of liquid, but I'm using different units. And just because this one is taller doesn't mean it's more. You guys can understand that as 6th graders. Why?
Because we're smart. 6-year-olds.
Still haven't got a good answer yet.
We got taught that along the road.
Well, what is it that you said you got taught? Like, what is the concept here that says, hey, this is not necessarily more just because it's taller? Yes! You understand what volume is, and it depends on the container, sure. Okay, but they can hold the same amounts. So all I did here was convert 12 quarts to 24 pints. Okay? And then we can clearly see 24 pints is greater than 17 pints. Okay? So all we're doing here, I don't want to make this harder than it has to be. You might think it's harder than the examples in the book, but this is the method that you're going to be able to use and depend on even after this class, okay? So this is called a conversion factor. Where do we get conversion factors from? Tables of equivalency. Fancy words for what does that equal, okay? So a conversion factor is something we multiply by to change from one unit to the next. Did it change the amount of liquid? No. 12 quarts is equal to 24 pints. So they're equal, it's just a different type of unit. Okay? All right. Lesson 78, piece of cake, right? Yes. Well, maybe we should talk about lesson 79 next. So, lesson 79, totally different change. Area of a triangle. Okay, quick recap. What is area?
The times length.
All right, so we got a formula, length times width. What were you going to say, Adeline? Like, what is it actually?
Well, the shape and if the amount of squares or units in it.
The number of square units inside a shape. Please don't reread this and say hashtag square units.
Hashtag
Okay, that's a sign of maturity, doing exactly what I told you not to do. All right. So we know this already. Length times width. Some people say different words. What are maybe two other words instead of length times width that they say?
Width times length.
Okay, that's just a different order. Same words, different words that might be applicable to a different shape.
Where?
Base times height.
Yep.
What would the square formula be, McKenna? They don't have different lengths and widths. You see the side's the same. So what would that be? Too many times. So what if I just did s to the second power? What would that mean?
Revolutionary times.
Side times side.
Oh,
You're reaching there.
Length times multiplication.
All right, good. Repeated multiplication. Good, Liam. Okay, so this is what we know, right?
Which is basically just
And this is related to shapes that have right angles. So, for example, this shape, which based on these markings has to be what kind of shape? Yes. Why didn't you say parallelogram?
Because of side.
sides are
Yes, they are. They have to be because of right angles. You said rectangle because of the right angles. Is it a parallelogram also?
Yes.
You don't know this yet, but because of these angle relationships, yes, it also has to be a parallelogram. But you should know, however, if you said rectangle, then yes, it is a parallelogram. All right, that's about 10 lessons, 15 lessons ago. Anyways, how would you find the area of this rectangle?
Length times width.
All right, so let me. You want to put some values in there? Nah, let's just do L and W. I like it.
You know how much it is.
No, you don't. You can do it with. Well, if you want the number, sure. But if you want the method, this is all you need. Now,
Just give us a line as a side.
all right. Well, I'm not going to do that yet. You'll see why. You see the shape here is a rectangle. The entire area is length times width. So, what does this diagonal dotted line do to the shape?
It turns into a rectangle.
It does what?
It turns into a triangle.
Turns it into a triangle. Can you make sense of what does it do to the area of the rectangle?
It cuts it in half.
It cuts it in half. Does anybody else agree with that? So are you saying that it could be as simple as 1/2 L times W?
Yeah.
Yeah.
Yeah, it could be
Yeah.
1
Yeah.
L
It's half.
times 1.
I'm going to put a little multiplication symbol in here. I'm also going to remind you that you could also rewrite this as base times height divided by 2. See, multiplying by 1/2 is the same as dividing by 2. So we just used the rectangular area formula to derive the area of a triangle. So let's do a couple examples, and then we'll move on, because I think this one is pretty straightforward. Have you seen the area of a triangle formula before? Or is that new?
Yeah.
You need me to turn that off? It's not warm? Okay.
Oh,
No, it's fine.
I have my hood on. Yeah, well, maybe you should move that so I know. No, please. You have to go all the way over there. No, it's really like. No, you move that table.
No, I did that.
So, you
I
moved
did
it
that.
over more, though.
I did that. All right, so there's your first triangle. Is it just not cold out? I mean, it's steam. Oh, it doesn't tilt any. Is that better? Okay. There's not. I'll change it. So I gave you some values. I might have. Does it mess you up when the triangle is all turned?
That doesn't even look like a triangle. Look at this cheese.
Well, here, let me make sure. Let me make this dotted, okay? Because otherwise you're going to think, well, it's like two triangles, right?
No, it looks like half a square.
So, how do you do that? Well, let's remember area equals base times height divided by 2. So, what is the base? The base is, which of these is the base? It is a 12. And then the height, so I've given you an example of something without fully explaining it. The height of a triangle has to be perpendicular.
It's 8. 8?
Hang on, it is 8. Yes, the height. I want to write this because I want you guys to write it. I'm going to put a synonym in here. Altitude is always
6 times 6.
perpendicular to the base. All right, so I also did a symbol in here. Shame on me, I just didn't want to write the word perpendicular, okay? No, it's really good for you to see. The symbol for perpendicularity, that could have been like a 4th grade spelling word, is an upside down T.
What, perpendicular?
Yeah, perpendicularity.
I can't even spell that. Perpendicular.
All right, so let me restate what I've written here. The height of the triangle, which is also known as an altitude, okay? The height of the triangle, which is also known as an altitude, is always perpendicular to the base. So maybe, you can turn it and see it. Oh, there it is, 12 and 8, right? But I show you the perpendicularity using the right angle symbol. Okay, so the area of this triangle, base times height divided by 2, we point out that the height is 8. So that would be 12 times 8 divided by 2, or 48 square units. So I didn't give you inches or millimeters or anything like that. Maybe I should have, but I'm simply reminding you that what Adeline said, area is the amount of square units that fit inside of shape, two-dimensional shape. Okay? So if that's the case, huh?
That base, because it looks like
Yes. The last word is base.
I did it.
So then let's come to something like this one. Yikes. Yikes, my friend. So let's give this a value of 12. What else do I need here to be able to find the area of a triangle? I need a height value. What I want to point out in this example is that the height that we draw isn't inside the triangle. The reason is it doesn't correspond with one of the vertices. You see, the same way this one was perpendicular to this base of 12. Okay? This one's got to be perpendicular. So I can't make that the height. This side cannot be the height. It's not perpendicular to the base. So here's what I got to do. I got to have like a little dotted line over here. I got to show that it's perpendicular. And then I got to have a value. So let's make that one 7. So now that we have that established, the 7 is outside of the triangle, but it is measuring something about the triangle. It's measuring the height perpendicular to the base. That's the value we have to have. So our area will be base times height over 2, 12 times 7 over 2, or 42 square units. So I'll stop for a second, make sure we can absorb all of that. Not all the triangles are going to be super simple and easy to see, although the method is still going to be the same. We have to make sure that the height that we use is perpendicular. There's that symbol right there. Perpendicular to the base. Okay. When you look in the examples, you'll see the examples that are just like that.
Instead of timesing it times 12, could you just times it by 6?
Mm-hmm.
That's just easier.
That's fine. That is fine. Question so far? Nah? Nah? Everybody caught up here? Okay.
Wow. It's cold here. Then put your hood up.
Yeah, I'm only half done. You okay? All right, so lesson 80, we're going to start with a simple data experiment, okay? I heard the pages turn, right? You're saving that empty space for the homework problems. All right, good. If you forgot, it's okay. That was your reminder. Lesson 80, okay? Scale factor for ratios, okay? So let's do a quick little data collection experiment. All right, so how many boys do we have in here?
4.
That's sad.
Yeah.
5 boys. Okay. 5 boys. So because there are 20 students in here, that means there are
15 girls.
15 girls. All right. Great. Now,
There's only 14.
is there only 19? Oh, okay. That makes this more difficult, but whatever. No, it doesn't. It doesn't change it. Shh. Okay. So 5 boys for 14 girls. Now, that is a ratio, isn't it? I haven't written it as a ratio, but I can write one thing. Who's doing the beeping? I'm going to write a simple symbol here, and now it becomes a ratio. Can I tell you something, though? It's not really as easy to work with the ratio that way as it would be for me to write it this way. 5 boys to 14 girls. So that's a ratio. A ratio is basically just a fraction that compares one value to another. I'm basically dividing, aren't I?
Sure you are.
Okay. So let me ask a question. If every class has the same ratio in a school of 60 boys, I just made a number up, okay? How many girls attend the school? Yikes. How do you do that? Okay, so let me regurgitate that because my handwriting's pretty bad. If every class has the same ratio in this school, where there's 60 boys, how many girls attend the school?
166.
How'd you get that?
Because if there's 60 boys, that means that if 5 was times by 12, and I did 14 times 6 times 2.
All right, so you use multiplication here, right? And what'd you say you multiplied by?
Well, I multiplied 14 times 6 times 2.
Times 2?
Instead of doing it by 12.
Oh.
I just halved it.
Okay. So that's what I'm getting at. Your work seems right. Let's get that right answer here. So what she's saying is, she noticed that 5 boys to 14 girls is the same ratio as 60 boys to some unknown amount of girls. Okay? So, what did you have to multiply again by? 5 times what?
12.
12. So 12 was a scaling number, a scale factor. Is 5/14 reduced as much as possible? Yeah. Yeah, it is. But the actual size of the school has to be magnified by 12. How do you see the 12? Well, what do you have to multiply by? You just look from 5 to 60. That's going to be times 12. So I have to do the same thing over here. It's times 12. That's one way to show you that there will be, we're just at 166?
Yeah.
I think it's 168.
Oh, that's what I meant. Yep.
168 girls. 168. What I want to point out here is whatever you had to multiply by, that's going to be called a scale factor. Now, you might not normally see that in a problem like this, a word problem. You're going to see it a whole lot more. Question. In geometry and visual problems, so let's try that. Let's try an example of that. Okay, 80.1. Let's say Grayson goes for a walk. And probably the opposite. If you going for a walk. Anyways, let's say he makes a map of his walk. And his map has 10 centimeters here and 14 centimeters here. And I'll ask you, how far did he actually walk if 1 centimeter is 200 yards?
No way.
Not that far. He ran. He could do it. So, no. 200 yards it is.
That's only 2,000 miles. 2,800. What are we trying to do? 28,000.
We're trying to figure out how far he actually walked. So this is Grayson's map. He decided he would log it, or maybe he's looking at an iPad with GPS while he's doing it. I don't know. Okay, but what I do know is that it's a scaled picture of what is actually happening. Scaled is just a mathematical word for magnified or the opposite of magnified.
Wait, is it not scale is just where keeping time? This is a different question than we're talking about, but is it 2 feet equal a yard? Or not 2 feet, 3 feet equal a yard? Or
3.
yard?
So, here's what we have to think about. If 1 centimeter equals 200 yards, how far do we actually... You want to draw the actual event and not just the map of it? Then 1 centimeter was equal to 200 yards. I'm going to take 10 centimeters and do what with it? Multiply. Multiply by what? I'm going to multiply by the scale factor. You see, we actually did a scale factor in this problem. It was right there. Okay? But this one in particular, because it says 1 centimeter is equivalent to 200 yards, I'm going to rewrite that as 200 yards is equal to 1 centimeter. Now, why did I do it in that order? Because I want the centimeters to do what? Cancel. I want them to cancel because I want my new units to be in yards. So 10 times 200 is 2,000. Now this is yards. And then I'm going to do the same thing for 14 centimeters. 14 centimeters times 200 yards in 1 centimeter. Okay? The centimeters cancel, and I'll get 2,800 yards. And so he walked a total of, he actually walked 4,800 yards. That's strikingly close to a 5K. A little short, but 4,800 yards. So let's look at the math here before we finish this lesson up. The scale factor told us what?
Grayson did not walk that much.
The scale factor told us what?
How to do it.
What to multiply by. Okay? The scale factor tells us what to multiply by. So, just like in lesson 78, it was a conversion factor. It told us what to multiply by. It helps us change units as well when that is necessary. Okay? When that is necessary. So let me go to a quick problem on delta math. Huh? Yeah. I'm going to go to a quick problem on delta math that shows you an example of what your scale factor problems are going to look like. Okay? We could convert 3 feet to how many inches?
Or you said 30.
36. And then say 36 plus 17, that's what, 53 inches. And then express that in feet, comma, inches. What would that be?
4 feet.
4 feet,
5 inches.
5 inches. Now,
Or, hear me out. You minus 12 from 17, and that's a foot. And then you add 3 and 1, and that you get 4.
I like it. Okay,
And then
okay.
you
3
get
feet
5 inches.
plus 1 foot plus the 5 inches that didn't get added. No, that's great. That's
what I said.
good. I'm not telling you anybody's wrong. I'm simply showing you, hey, there's 2 ways to think about it. Now, you might think, well, that was too much work. Don't be lazy. All right? But it doesn't mean this is either one are wrong. They're both correct.
Work smarter, not harder.
Okay, well,
Why do you
let's
think
make
so
sure. So I have one other situation. And this might kind of seem unrelated, but it's in Lesson 81, so I want to make sure I take a look at it. I drove 351 miles on,
Tuesday.
let's make it 16, sorry. 361 miles
On Tuesday.
on 19 gallons of gas.
Well, why
Okay.
you do that? It's so dangerous. I don't. How many miles can a gallon of gas do?
Oh, wait. What question are you asking?
Oh my god. How many? That's literally one. Okay, never mind. It's not that dangerous. I just thought it was like.
What is the miles per gallon value?
What do you mean value?
Number.
Yeah. Oh.
If I can drive 361 miles on 19 gallons of gas, the question says, well, what is the miles per gallon value? First thing to recognize, miles per gallon is a what? Yes, it's a ratio.
That has
We
to be
also can call it a rate.
division.
Well, that's basically the same thing. Oh, that third thought. A ratio is a rate. A rate is a ratio of one quantity to another. And because it's a ratio, McKenna's right. She said, you're just going to divide. How do we know what order to divide in? How do we know what order to divide in? It's in the sentence.
306, the bigger one. You know,
Miles divided by gallons. It doesn't have to be the bigger one over the smaller one. Stay with me, guys. It has to be in the order that the question was asked, because the order of division does matter. So the miles, which was 361 miles, I'm going to divide by 19 what? 19 gallons. Now, look at what my answer is going to be. I can tell that I'm doing this correctly because of the order that I see it in. Miles over gallons. So, anybody?
We're doing it right now. Yep.
Okay. Miles per 1 gallon. Or 19 miles per gallon. Is that right? Yeah, that's right. That's right. It's okay. How does it apply to what we're doing here? Well, lesson 81 is about arithmetic with units. So the question tells us, right in the question is the clue to what order we do this in, what units we're supposed to use, and what the meaning is. What could I then turn around and use that to find, okay, if I ask you a multi-step question like, okay, so how many gallons does it take, let's say we're going like a cross-country road trip. How many gallons does it take to drive 1,100 miles? Okay? So, you think, isn't there like computers to do this for us? Yes, sure. Somebody had to program those. Somebody had to know how to do this in the first place. So, and somebody has to know how to use this camera. It's not me. We could use this value to then determine how many gallons will it take for 1,100 miles?
19.
And that's your extra credit opportunity for a homework pass.